Good afternoon. I'm Eshed Ohn-Bar. I'm an assistant professor at the EC department here at Boston University. I'm very excited to welcome you all to this event on bridging AI and disability. This event is part of a much larger interdisciplinary effort on teaching machines human-like intelligence at the Boston University Rafik B. Hariri Institute for Computing. So I definitely want to thank the Institute and Boston University for helping supporting and helping organize this event, particularly Catherine D'Angelo in helping to get everything organized. And please note that this event is being recorded. Assistive AI has the potential to address urgent accessibility and quality of life needs for individuals with disabilities, from descriptive video narrations and assistive navigation and up to robot-assisted rehabilitation. In this event, our goal is to broadly explore directions for user-driven AI frameworks, specifically in the context of assistive and rehabilitative technologies. We will explore paradigms that can efficiently and robustly enable various AI tools to meet the diverse needs of end users with disabilities. On today's agenda, which is shown here on this slide, we'll have 4 featured speakers. Each talk will take about 30 minutes, followed by 15 minutes of Q&A. If you do have questions, just enter them in the Q&A feature in the Zoom, and we'll read them out at the end of the talk. The talks will be centered around topics related to accessibility and AI. So first we'll have Dr. José Millán, from a professor at the University of Texas at Austin, speak about translating brain-computer interfaces to people with disabilities. We will then have Dr. Patrick Carrington, assistant professor at Carnegie Mellon University, speaking on understanding everyday challenges to create accessible experiences. At 1:30 p.m., we'll have Saqib Sheikh, manager and project lead for Seeing AI at Microsoft, talking about Seeing AI, empowering the blind community through artificial intelligence. And our final speaker, Dr. Maya Matarik, distinguished professor at the University of Southern California, will talk about a robot just for you, socially assistive robotics for personalized, adaptive social support of each user. We'll then have a speaker panel and conclude. So once again, I want to thank the speakers for their participation and hand it over to the host of the first talk, Brian, Dr. Brian Kulis. Brian is an associate professor at BU, researching machine learning, statistics, computer vision, and large-scale optimization. He's also an Amazon scholar working with the Alexa team. Brian, the floor is yours.
Thanks, Eshed. So let me introduce the first speaker, Dr. José Millán. He is the Carol Cockrell-Curran Endowed Chair Professor in the ECE department at UT Austin. That's my old stomping grounds. His interests are in areas such as neuroprosthetics, brain-machine interfaces, brain-computer interfaces, neural engineering, human-robot interaction. He is also a professor in the Department of Neurology at Dell Medical School. He's made a number of different contributions to brain-machine interfaces. He's an IEEE fellow of the International Academy of Medical and Biological Engineering. He's going to be talking today on translating brain-computer interfaces to people with disabilities. So, when you're ready, Dr. Millán, take it away.
So, thank you so much for your invitation and the kind introduction. I am very pleased to share with you today the work that we are doing around this topic of how to transfer brain-computer interfaces to people with severe motor disabilities. So let me start by showing you different kind of robots, that brain-controlled robots that we have developed over the years. that have been tested originally by people who doesn't have any kind of disability, so able-bodied people, and only afterwards that we have been tested them exhaustively, we have then transferred that technology to people with disabilities. So I will be showing you a few examples of these robots, and then I will also show you examples of how this technology can not only be used for assistive devices, but also for designing novel neurorehabilitation interventions. So as a very quick reminder, this is the architecture, the basic architecture of a brain-computer interface or brain-machine interface, where we will need to record in real time with a portable wearable device brain electrical activity that is the most appropriate for fast decoding of people's intents in order to transfer them to actions of an external device. These signals, the electroencephalogram in this particular case, that it is the most common signal that we are using because we want to reach a large number of users, and we have been working already with over 1,000 people, more than 200 with severely conditions. These signals have a signal-to-noise ratio that is quite low. They are quite non-stationary, and yet we can significantly have modulations of those signals in certain embedded subspaces of the whole brain electrical activity. So the question is, can we identify which are these transformations that we need to do in the raw signals in order to transfer them to an appropriate representation, and once there, how to identify those dimensions that are more relevant for encoding that intent of the person, so that afterwards we can build models, and these models will eventually recognize which is the intent of that person at that moment, at that place, so as to transfer, to translate or to transfer this intention into the proper actions of a device. And finally, we need to close the loop, because otherwise, if the subject doesn't receive feedback of how well their brain-computer interface is decoding their intentions, they cannot learn how to modulate those signals in order to convey better and better their intents. So this means that we are facing here a double learning agent process, what it is called mutual learning. Because on the one side, we want our decoders to learn which are the representations of brain signals that carry the user's intents. But on the other side, we want that through this feedback provided by the brain-computer interface, people learn volitionally how to modulate those signals. And now this process has to converge. Otherwise, neither the machine nor the person can have a good understanding of each other. So I will start by this point over here, illustrating one example of how this process of mutual learning take place. And this mutual learning, I insist, is about how machine learning can support human learning. So the first example is taken from an international competition in which we participated a few years ago. This is called the Cybathlon. Maybe you have heard about it. Cybathlon is similar, if you want, to the Paralympics, in the sense that we have athletes. These athletes have to compete in races. But the difference is that the complexity of the races is such that for people with severe disabilities, they cannot accomplish the race if it is not with the support of an assistive device. So the point is, how can we promote the development of better and better assistive devices that people can use in real life conditions. So one of the races was the brain race. In this case, the athletes that qualify for the race have to be tetraplegic people. We competed with 2 of them, and we were training them over months. And what is the race about? So what you can see over here is that there are avatars. Each avatar is associated to one of the athletes, and they are controlling the speed at which the avatar is racing by delivering brain commands. You can see also that the race is composed of pads of different colors, so that at every color, the athlete has to deliver the appropriate motor brain command. So this means that if they deliver the correct command, as soon as the avatar enters into one of the pads, the avatar will accelerate. If they fail because they deliver a wrong command, then the avatar will slow down. And finally, if they don't manage to deliver any command, the avatar will simply keep moving at the normal pace. And remember, this is a race, so we want to have not only high decoding performance, but also fast decoding performance in order to deliver the correct command as soon as possible, so as to accelerate most of the time along the race. So let me briefly show you a key of the performance elements during the training of these subjects. So you have here subject 1 to the left, subject 2 to the right. This is the BCI performance, how well the decoder was able to decode the intended command. And I forgot, there were 4 pads, color pads. So how well the BCI was decoding. And you can see, take subject 1, that at the very beginning, during quite a few weeks, his performance was not particularly good. During this period, we wanted to reduce the number of times that we were modifying. Actually, during the whole training process, we reduced the number of times that we were modifying the parameters of the decoders. Why? Because we know that people need time to adapt to the feedback that they are receiving. So if the decoder is changing too quickly, they don't have time to learn via operant conditioning, which is the proper modulations that they need to engage onto in order to deliver the correct commands. But you can see so that very quickly, the subject, very quickly, after a few weeks, all of the sudden performance started to improve over time and then stabilize at the very end. The case of the second subject also shows this improvement, longitudinal improvement over time, even if his performance was already higher since the very beginning. This is a race. So the second component is in any learning process is how well you perform a task. Second is how fast you perform the task. And you can see that if we take during the training time period, the first sessions where they were training to run these races, as compared to the last races that they did during the training, there is a statistically significant improvement. They were effectively learning because performance was higher and time was shorter for both of them. But the most interesting aspect of this process is that if we start analyzing the modulations that they engage volitionally in order to deliver the different commands, and here I am showing you how well every single area of the cortex that we were monitoring was capable to differentiate the different commands. You can see that let's take subject 1, that yes, we could observe a light modulation, discriminability, so that the performance was better than random, but not great. But as the subject trained, performance, so the discriminant elements of modulations started to change, to converge on certain modulations, and then grow stronger and stronger. And then it remained very stable for the last period of their training, including the day of the competition. And this is also the case for the second subject, that was capable to learn those discriminant modulations and keep it very stable, including the day of the competition. And by the way, during the competition, one of the subjects won the gold medal and the other established the record time of the competition. Let me move on to another example of an assistive device, in this case with a physical robot, a wheelchair. This is a study that we completed recently in a clinic, a rehabilitation clinic in Germany, Bochum. So in this case, we recruited 3 tetraplegic subjects. One of them, for example, this one had a very high level of spinal cord injury to the point that he required assisted ventilation. And we trained them to drive the wheelchair in a natural environment, an environment that for them is a familiar environment. It is actually the rehabilitation ward that they need to go to regularly in order to maintain their physical condition. So here I am showing you a schematic of the task and the performance that they achieve in this task. So the task for them was to drive the wheelchair that started always in this bottom bottom right side of the rehabilitation ward. And now the wheelchair had to go through a few waypoints in the order that they are indicated: waypoint 1, waypoint 2, waypoint 3, waypoint 4. In black, you see the ideal trajectory if we take into account the quality of the trajectory, usual criteria in robotics, like fastest and shortest path that go through the waypoints while maintaining a certain distance, safety distance to any obstacle in this environment. And now the colors that you can see for any cell in this environment indicates how many times, because they were driving the wheelchair several times during the testing, how many times the 3 subjects went through that particular cell. And the warmer the color, the more often they went through that particular cell. And now you can see that there is an emerging pattern that is this yellowish color that you can appreciate. That is the most common pattern that they were following. And you can appreciate also that this actual path, average path that they were taking was relatively close to the ideal path. And we were not telling them this is the ideal path. All the instructions that they receive is do it as fast as you can, as safely as you can. So, of course, during the training, what we observe is not every subject perform equally. So we know that during the training, before coming to perform the final robotic navigation, wheelchair navigation, subject P1 was performing better or achieve a better performance than subject P3, and subject P3 better than subject P2. So let's take a closer look at those measures and let's try to correlate everything with respect to their final performance. What we can see is that subject 1, if we only look at the performance of his BCI, was improving dramatically during his training period. Subject 3 had also some learning process, except that at the very end, he decreased. And one of the reasons that we believe he decreased at the very end was that in this process of trying to tune the decoder to the brain signals that the subject was exhibiting as the most discriminant, at the very end, this process didn't converge very well. And this is why when we return to the previous, and by the way, these lines, vertical lines over here, indicate how many times we were recalibrating the decoder. So you can see that there are only a few sessions. The rest, it was fixed. So at this moment, we return to the original decoder that was used at this session, and the subject recovered performance. The third case, subject P2, was a particular one, because this subject had a very good performance since the very beginning, actually the best performance among all of them. And you can see that his performance was flat. He was not capable to improve performance. Performance was good, but no sign of learning. If we now take this view, internal view of the features that they are modulating and how discriminant are they in order to differentiate the commands that they want to deliver to the wheelchair, we can see that for subject 1 and 3, this index of discriminability grows, meaning that they are capable to generate better and better brain signals that will convey better and better their intentions. Whereas for the case of the second subject, who didn't improve his BCI performance, he couldn't either learn how to modulate better his brain signals. And finally, since one of the criteria was how fast, how smooth they can control their wheelchair, we can measure how well they were modulating brain signals as compared to how fast they were capable to deliver correct commands. And again, what we observe over here is that for subject 1 and for subject 3, we have a positive, significant, well, actually, it is a negative significant correlation, because the better they were capable to discriminate, the faster they could deliver commands. Whereas for subject 2, who didn't exhibit any sign of learning, this correlation was not significant. What reinforces the fact that in order for people to be able to control efficiently and to learn to control efficiently a brain device, they need to go through a longitudinal training. And unfortunately, this works for most subjects, but not necessarily for everyone. So the question is, how can we improve this learning process supported by the use of machine learning in order to promote this user learning? Let me move to the last part. Well, there is still 2 parts, but I want now to emphasize how the lessons that we are learning as people use assistive devices, brain control assistive devices, may transfer and is being transferred to the field of rehabilitation. So one of the major conclusions that I have been trying to convey today is that as people use over long periods of time or sufficiently long periods of time a brain control device, they learn how to modulate their signals. They are changing the modulations that they volitionally engage onto. And this means that if you are able to change your brain rhythms, this has to be supported by some kind of plasticity process. And if we can, and so if the use of a brain control device induces brain plasticity, then we are opening the door to using brain-computer interfaces for rehabilitation. Now I would like to show you one of the studies that we have done with chronic stroke patients, and I will define in a moment what I mean by chronic. The idea is that if we want to promote maximal plasticity, we need to somehow follow the we need to be inspired at least by how we use in a healthy individual, how motor control is performed. And motor control requires modulations that start at the cortical level, and these modulations, these signals are being transferred via the corticospinal tract and all the subcortical areas that are contributing to refining the parameters that the motor cortex are sending down the corticospinal tract until they reach the periphery, so that they engage and provoke a muscle contraction that executes your intended movement. But at that moment, we also receive a substantial amount of proprioceptive feedback that is ascending to the different components of the motor network in our central nervous system in order to not only inform that the intended movement was executed correctly or incorrectly, but also to promote plasticity so that we learn how to modulate our brain signals in order to achieve desired behaviors. So what we can use then is to have a brain-computer interface that will be decoding the intent of a person, eventually paralyzed, at the level of the hand, because this person will be modulating patterns of activity that not necessarily are the healthy ones. And once this intent is decoded, we can transfer it to the periphery in order to execute the movement, replicating the natural pathway of the descending commands. How we can stimulate, and you can see over here, these electrodes, we can stimulate via electrical stimulation the peripheral nerves that will induce the desired contraction. In this particular case, it was the extension of the wrist and fingers, something that stroke people with severe paralysis can't do by themselves. So the study that we conducted, we recruited 27 of these chronic stroke patients, meaning that they were at least 10 months after their stroke in a stable condition, meaning that they were not recovering more function, as we were assessing in a few evaluations before they were recruited for the study. Now, 14 of these subjects went to the group, to the experimental group, where detection of the motor intent to make the hand and wrist extension induced the stimulation, peripheral stimulation. And 13 of them were our control group, our sham group. And what sham means in this case? Sham means that they were using the same apparatus, they were receiving the same instructions. The only difference is that hand stimulation or peripheral stimulation was random. They were not concomitant, they were not linked to their actual brain state. So at the end, they were both groups were receiving the same amount of stimulation. The difference is that in the first one, we were coupling, the stimulation was contingent to the activity in the brain, whereas in the second was random. So this was a 5-week intervention, and very quickly, let me show you the main clinical outcome. It is in terms of the Fugl-Meyer score. Fugl-Meyer is an index of function, so that the higher, the better. You can see that at the very beginning, before the treatment, both groups had the same Fugl-Meyer score. But after the 5 weeks intervention, only the BCI group improved and improved significantly. Not only improved significantly, but also the amount of improvement was clinically relevant, meaning that since they recover more than 5 points, they could do functions that they couldn't do before. And more significantly, we, after this evaluation, immediately after the end of the intervention, we send them home and we call them back on average 9 months after the end of the intervention. And you can appreciate over here that whatever they recover was maintained after 9 months. So what changed in their brain that can be an explanation for this functional improvement? Well, one of the things that we discovered is that if we measure the connectivity index inside the damage motor area for each individual subject, so everyone will have the damage either in the left or the right hemisphere, but we are flipping, if it is necessary, everyone so as to have them all on the same side. What we can observe is that when we compute the amount of information that is flowing inside the damaged cortex, this is what this connectivity index is telling us, we can observe that at the very beginning they had the same level of connectivity, whereas only the BCI group increase that index of connectivity, meaning that there is more information that is flowing in the damaged hemisphere as they engage to perform the task, to perform a movement that they couldn't do. And this is not an explanation, this is not a causal relationship, but we can also see that there is a correlation between improvement in Fugger-Meyer function and increase in connectivity index, how much information we are reactivating inside the damaged cortex. Let me change gears to show you the last element of the work that we are doing, because we not only need to exploit explicit motor commands that people want to deliver to, say, a robot, a wheelchair, to use a brain-computer interface. Because in fact, whenever we are engaged, say, in controlling a wheelchair, no matter how good is our brain-computer interface, because of the nature of the brain signals that we are dealing with, we cannot guarantee 100% performance all the time. Sooner or later, we will be making mistakes. So that subject wants to deliver command A, the brain-computer interface recognizes command B, but as soon as the subject starts receiving the feedback that, for example, rotation of the wheelchair of the decoded intent, and they realize that this is an incorrect decoding, everybody is aware that this is an erroneous decoding. The important thing is that we can decode correlates of this awareness to errors made by the brain-computer interface, like those modulations over here, 100 milliseconds after this wrong action is started to be executed. And now we can exploit those, what we call error-related potentials, in order to improve the performance of the brain-computer interface, or, and this is the topic I want to cover in my last couple of minutes, to, rather than requesting subjects to learn how to modulate signals in order to control a complex system, why not to exploit the fact that via artificial intelligence, we can build autonomous learning agents that can learn from the experience. The important piece of information that we need is a reward signal that will be telling the intelligent controller when they are doing things right and when they need to explore new actions that will be better for the state the agent is at any time. So this is exploiting reinforcement learning that is a standard technique nowadays, using the human as the source of reward signals. So what I will show you in a moment is the case where we want to teach an assistive manipulation system that is capable to move objects in a table for us. The subject may eventually initiate with a very limited residual ability the movement of the manipulator. They can eventually generate very coarse demonstrations, but given their limited residual ability, these demonstrations will never be perfect. So the question is, can we learn from these demonstrations? Actually, in our case, it is a robot, an armed robot, that using dynamical systems can generate different kind of trajectories characterized by how fast they will start avoiding any obstacle on the way to the target, how much clearance they will be keeping with respect to the object. And what we will be requesting the subject is simply to monitor the quality of these trajectories, so that whenever they consider that one of these trajectory is not a correct trajectory, because eventually this will lead to a collision a few milliseconds later, we can observe modulations, error-related potentials that we can use as a weight that will be associated to that particular trajectory, and then we will be using inverse reinforcement learning algorithms in order to infer the desired trajectories. And now the relevant, so this is feasible. People can program or teach actually their assistive devices how to perform those avoidance of objects while manipulating others. What emerges is that every single subject will have a preferred kind of trajectory. So this means that we can over here uncover the personalized robot behaviors that every single subject may prefer. And this is done on the fly as people are interacting with the robot. And finally, once they have taught the robot how to perform the avoidance of one single object, they can start interacting with a complex setting in a table, on a table, so as to manipulate different objects from point to point in the table. I stop over here. Thank you for your attention, and I will be now happy to answer any question that you may have.
Thank you for the talk, and for those of you that have questions, there's the Q&A feature in Zoom. If you can put your question in there, then we'll see it, and then we can ask the question. So in the meantime, let me ask you a question. So early on in the talk, you were talking about the wheelchair moving, and you talked about how different lengths of training impacted how well they were able to do the trajectory. So I'm curious how this training actually works. So is this like assisted training with someone prompting them what to say, think about, or how does that work?
A very great question. I didn't have time to enter into the details. So yes, at the very beginning, it was a supervised training where subjects are sitting on the wheelchair, and they are requested to deliver a right command, a left command. At the very beginning, the chair is in a static position. It doesn't move. So after decoding left or right, the wheelchair will simply rotate so that they can get used to this first easy, between quotes, task. Then in the second phase, the wheelchair start moving in an open environment so that they are not disturbed by any potential collision with any obstacle, and the interface will be asking them deliver left, deliver right, so that now while the wheelchair is moving, it is start also rotating, so that they get used to the kinematics of the experiment. And only afterwards they move to the real navigation, avoiding obstacles. And in the last evaluation, they are not told what they need to deliver. They need to figure out which is the command that they need to deliver in order to go through the ideal path as they consider it is ideal.
See, thank you. I see a question. This is from Eshed. Do you observe types of users and strategies during the adaptation process where perhaps these can be identified to facilitate faster adaptation?
No, we have not been able, because people are very bad to tell you what they are doing. They are saying, yeah, I imagine this hand movement or this foot movement, but they are very bad to describe exactly what they do. Furthermore, even if at the very beginning we are telling them in order to control, and I forgot to mention that, try to imagine movements of different parts of your body, your left hand, your right hand, both of your hands and your feet. Because we know that our brain has a representation of our body. So we know that simply by attempting to do a movement, even if this movement cannot be executed, we will be modulating the corresponding limb part of our motor cortex. And this is what we intend to decode. So they start imagining this, but as they learn, there is a moment where they don't think any longer in terms of their body. They think in terms of their device that they want to control. So that now they are simply saying, in the case of the wheelchair, wheelchair left, wheelchair right. What it is, I mean, we don't have yet evidence, especially with non-invasive approaches and in humans. In animals, it should be easier. But we don't have evidence that they are incorporating the device as an extension of their body, even if there are different elements that are pointing to that fact, that they are incorporating this device as an extension of their body. But how this happens, we don't know.
All right, thank you. So we have another question here. How much does learning the mapping from EEG signals to actions from one person apply to another person?
Well, unfortunately, this mapping seems to be individual because the patterns of activity that we, no matter whether you are implant electrodes or you use EEG, as in the examples that I have provided here today, the patterns of electrical activity is due to the patterns of synaptic connections that we have in our brain that will be modulating neuronal populations. And this means that these patterns of synaptic activity, of synaptic connections, is individual, because these connections will grow or disappear depending on your individual experience. And since every person will have a different individual experience across their life, this means that even if you are moving the same finger that I am moving, the neuronal population that you are engaging to do so will be different than mine. So transfer is an open question. I hope we will be able to report soon. But in principle, you need to personalize. And this, even if transfer is possible, you need to personalize.
Right, thank you. Okay, we have another question here. Can this therapy experimentation help people with severe nerve damage?
Well, that depends on what you mean by nerve damage. If it is peripheral, I don't see right now how. if it is a lesion of a part of the central nervous system, including the spinal cord, there is always the possibility that this contingency between descending and ascending volleys of neuronal activity converges on certain areas across different pathways, so that we can reactivate unusual pathways in a novel manner, so as to transfer over those alternative pathways functions that were originally encoded in the damaged parts of the central nervous system. I mean, this is a very bold hypothesis. Now we need to prove it, but there is more and more evidence that this is happening for different kind of conditions.
All right, and let's see, maybe we can do one more question since we're just about out of time. Let me see here. Someone asks, can the function simulation of a specific part of the brain map be transferred to another limb of the body?
Well, theoretically, yes, because if you induce this kind of activity-dependent plasticity that I was talking about, so imagine that you want to transfer from your left to your right hemisphere, what you will require is to provide feedback to the person so as to modulate symmetrically this pattern of activity over here, and this will be giving reward eventually, for example, by moving a part of your body. So according to the principle of activity-dependent plasticity, according to the principle of operant conditioning, sooner or later, the person would be able to learn it. The question is how long it will take, and probably it will take very, very, very long, because this is a completely new representation that has no association to the body schema that we have in our motor brain.